Hello students, welcome to Unit 9 Notes, Section 5.3. I have already done the warm-up for you to save some time, so if you printed this out or if you just have a separate sheet of paper, you can follow along. In the first column, I found the derivative of all of these items here, so the derivative of sine with respect to x is cosine, the cosine is negative sine is negative cosine. Remember the opposite here would be the opposite there, so that's where those two come from. And then the opposite of cosine, which is negative sine, gives you the opposite of negative sine, which is sine. All these y's become y prime. So f of x becomes f prime of x. It's really dy dx. And then in this column, I actually took the first column and found the antiderivative. So you go in reverse order. So what's the antiderivative of sine? Well, go backwards so if this is its derivative, work backwards and you get negative cosine. So that's why the antiderivative is negative cosine. And then what's the antiderivative of cosine? Well, that's going to be sine, right? Because the antiderivative of cosine is sine. So you're working, instead of going from sine to cosine, cosine to negative sine to negative cosine to sine, where the cycle starts over, you're actually going in the reverse order. So the antiderivative of sine is negative cosine. The antiderivative of cosine is sine. Antiderivative of negative sine is negative cosine. Antiderivative of negative cosine is negative sine. Okay, feel free to pause it and write them down, but I'm going to continue. I'm going to try to make this lesson as quick as possible, so I am going to skip some slides. Okay. Now, for the properties of definite integrals that's our topic today. So there's certain properties that they follow. Okay, properties of definite integrals, average value of a function, mean value, and connecting differential and integral calculus. So right here we have, let's take our integral. Notice that this one doesn't go from A to B, this one goes from B to A. That's a problem. So instead of creating area under the curve, let me do this. Instead of creating area under the curve from A to B, like we have been doing, so let's say from A to B, from A to B we have something. Here's our A to B. And we have some function. I don't know, I'm just going to graph a random one. Let's say that one. Instead of creating area under this curve, like this from A to B, we're going in the reverse order now. So we actually are what the area's been there. And what we're kind of doing is we're kind of erasing it as we move from right to left. So in that case, in theory, instead of creating area in a positive direction, we are now going in a, let me just put that back. We are now going in this direction here. So that yields us to actually be taking it away or to have some type of negative out front. Okay? So the Riemann sums ultimately is about taking those items away, subtracting them when you work in the reverse order. So we always want to go from left to right, which means that we have to change B to A to be A to B. And you're going to say, well, what is A, what is B? We want the lesser number. We want the lesser number to be down here and the greater number to be there. So they might be positive or negative, but again, let's say you have 5 and 7. You want 5 to be the lesser number and 7 to be the greater. So if it goes from 7 to 5, from 7 to 5, you want to change it to be the opposite of 5 to 7. It's just something that we have to do when we're computing these. Okay. Let me clean that one up. It's hard to see that's a 7. Okay. So here are some rules. We have the order of integration. Again, we want to flip it and make sure it's correct. So I'm going to draw examples for these. So let's say let's go with our 5 to 7. Okay. Now this one's in the wrong order, 7 to 5. So we're going to make it 5 to 7. Okay, let's say it was 5 to 7 of the function 4. So it's going to be the opposite of that. So if I were to graph this out, and I were to have from 5 to 7, oh wait, let me use the same colors. So from 5 to 7, and we graph the function 4. So here's the function 4, here's y equals 4. We would shade this area right here. And we would have created that area. Well, we're going in the reverse, so we're going to take it away. So in this case, instead of having a width of 2 times a height of 4, we're going to have the actual opposite of that. So we're going to have -8 as a result for area because it's being taken away. So this result ends up being, remember, yeah, so that negative is out front. So that's the negative I'm talking about. That's going to stay out front. Let's change that to that negative right there. And there you go. Okay, this one is pretty self-explanatory that this one is always equal to 0. That's because there's no width to this one. So let me put the work for this one above it. Let me copy this one and put this one, I'll put number 2 down here because I don't have much room. I'll label this one as 2. I'll label this one as 1. All right, so number 2, the zero rule, if I were to move this over to 5, from 5 to 5, notice there's no thickness at all. There's no rectangle. There's no figure there. So there's actually no area there. So if we go from 5 to 5 of y equals 4, the answer is just going to be 0 because there is no thickness to that. Okay? The constant multiple rule allows you to pull a number out front of any equation. So as long as it's factorable out of everything. So let's say that I graphed from zero, whoops, these are the wrong color. Okay, let's say I graph from 0 to 3 of 2x. That could be the same as 2, 0 to 3 of just 1x. They're equivalent. Okay, and I'll show you the graph. And the same thing for the negative. You can pull a negative out front. So let me graph the constant multiple rule. You know what? It would make more sense for number 2 to go up here. And now I'm going to do number 3 because I need 2 graphs for number 3. Let's say, whoops, let's say that we graph this one. So from 0 to 3, here's my 0. I'm also going to put 3 right here. So we have the equation y equals 2x. So it's going to go quite quickly. Let's say that this was 6 up here. So this area shaded, this area that's shaded here, from 0 to 3, and then from between the x-axis and 2x, that area is a triangle. And what you notice here is that you have 0 to 3 is 3, so it's 1/2. Area is 1/2 base times height, so area is 1/2 of 3 times 6, so area is 1/2 of 18, and so area is 9. Okay? Now, in the second example, I'm going to leave all of this here. I'm going to change the style of this line. It's no longer going to be y equals 2x, it's going to be y equals x. So it's going to intersect halfway through. So whatever we get for this answer, what we need to do is we are, in theory, instead of it being 2x, it's y equals x, which has a slope of 1, so it goes up 1 over 1. So it intersects at 3 now instead of intersecting at 6. So the area of this one is not as high as 6, but it's actually as high as 3. But don't forget, whatever I do to this, I need to, so we get 9, we get 4.5. Well, these areas are different because I factored out the 2. So now what I need to do is say that the integral from 0 to 3 of x times 2 out front dx. That's the difference. So this integral actually equals the number 4.5. So that is a total of 9. So the area here is 9. So I'm factoring the 2 out so I don't have to deal with it. Sometimes that's something you want to do. Okay? Whereas this one, the integral from 0 to 3 of 2x, I'm leaving the 2 on the inside, dx equals 9. Okay? Just some of the rules there. Sum and difference allow you to, I'm not going to draw diagrams, I don't think, for the rest of these. Well, maybe I will. Okay, from a to b, you have the addition, so you're able to break them into separate integrals, and that makes sense. So if I have, if this was 5, I'm able to break it into 3 and 2. So I can have separate ones adding to, let's see, if f of x plus g of x was equal to 5, I could do 3 and 2. I could do 4 and 1. I can really do I can break them up however I want because I'm doing both of them. I'm going to look at them separately. So instead of going up to 5, instead of going up to a total of 5 here and shading, I'm looking at it more in the lines of more in the lines of 3 plus 2 in the same amount of space. So that area, oops, plus this area in the same interval is equal to all of this area. So I'm just going to change my numbers. You can subtract them too. So I'm going to say 5 is equal to what's happening to 5 is equal to what's happening at 3 and what's happening at 2 between the same intervals. That's number 4. As long as they stop at the same location. Okay, and these graphs all stop at the same location. Now they don't need to be rectangles. I just find rectangles to be the easiest to explain this concept. And the last one, you're able to break intervals apart so you can add or subtract them. Okay, and so you can look at them. Everything that's happening from A to C. Let me do number 5. Everything that's happening from A to C. And I'll call this one A to B, assuming that that's where it stopped, A to B. So this one, I'll call this one A, I'll call this B, and I'll call this C. Okay, let me throw in a line here. Not bad. All right, everything that's happening here, everything that's happening here, you're able to break them up. So what's happening from A to B, and then what's happening from B to C is equal to the total of what's happening from A to C. Makes sense. You're just adding two separate areas together. Okay, so hopefully I explained these very, easily. We're just going to manipulate them today. Don't worry about number 6 and 7. Not worried about it. Not our focus. Okay. So let's go to our first example. We don't know what the function is, right? We have no idea. But what we know is that when we integrate it, when we find the antiderivative of it, -1 to 1, we get an output of 5. Okay. So ignore the function. You don't need the function. You just need to know that its area is 5. What we know is that from 1 to 4, the area of that same function is -2. And what we know what's happening from -1 to 1 of that function, oh no, this is a different one. Take a look. This one's different. These are both f of x. This one is h of x. So this one's totally separate. What's happening for that function is an output of 7. So now let's just manipulate these. So here we know that 1 to 4 has an output of -2. Well, this is 4 to 1. So what I first need to do is change it. So I'm going to go from 1 to 4. It's the opposite. Don't forget you need to throw a negative when you switch it, of f of x dx, which is equal to, now we're almost there, -1, because I pulled a negative out front. What's happening from 1 to 4? Think about that negative as being way out front, factored out front. Okay, what's happening from 1 to 4? -2. So it's literally that times -2, because 1 to 4 of f of x dx is -2. So I get a result of 2. So the answer to this one is 2. And we're done. All right, we have -1 to 4. So this is like saying, look at how I can add them together. We go from -1 to 1 and then 1 to 4, kind of like we did up here. So -1 to 1 and then 1 to 4. So I'm just going to add them together. So I'm going to break this into -1 to 1 of f of x dx plus 1 to 4 of f of x dx. So -1 to 1 is 5. So it's going to be 5 plus 1 to 4 is -2. And that equals 3. And that's my answer. I want to keep these as simple as possible. You're just breaking them apart, multiplying them, pulling a negative out front, flipping the integral and making it opposite. Okay, so this one is negative 1 to 1 of 2 of f of x plus negative 1 plus negative 1 to 1 of 3 of h of x dx. Let's break this apart. The first thing we want to do is do the addition rule here, and we're going to do 2f of x dx, and then we're going to do negative 1 to 1 of 3 of h of x dx. So break it apart first with addition. And then what we can do is we can factor out, in our next one, we'll factor out the 2. So it'll be 2 times negative 1 to 1 f of x dx plus 3 negative 1 to 1 of h of x dx. So now we have 2 times, what's negative 1 to 1 of f of x dx? It's 5. So it would be 2 times 5 plus 3 times negative 1 to 1 of h of x dx, don't mix them up, is 7. So we have 10 plus 21, which is 31. So this answer is 31. All right. Next one, 0 to 1 of f of x dx. 0 to 1 of f of x dx. Let's take a look. There is no 0 to 1. And because none of them overlap, I can't use subtraction and do anything. There's nothing that I can actually do. I'm looking. I don't see anything. Whoops. I don't know why that. I don't want that. There we go. I do not see anything that I can do. So this one does not exist. Not possible. That's okay. Some of these are not possible. Okay, so 0 to 1, definitely not possible. Okay, negative 2 to 2. You can't just take this and multiply this by 2 and multiply that by 2 and just say, well, that's 7 times 2. That's not the way these work. We don't know what's happening from negative 2 to negative 1, and we don't know what's happening from 1 to 2. They could be different, like I showed above, right? I showed that this above could be different. So this one is also a does not exist. Not possible. We could even say not enough info. Actually, it could be possible. We just don't have enough information to make it possible. Whoops. I'm talking and not writing what I should be. Okay. I actually like this answer better. Not enough info. It's actually the best. Okay, negative 1 to 4. We can definitely go from negative 1. We can definitely go from negative 1 to 1 and 1 to 4. But watch, we can go from negative 1 to 1, but there is no h of x from 1 to 4. So this one is also going to be does not exist. But here's what we're going to have to do to show our work. We're going to have to do a little bit of work here. So we're going to say negative 1 to 4 of f of x dx plus negative 1 to 4 of h of x dx, which, which broken down will be negative 1 to 1 of f of x dx plus 1 to 4 of f of x dx plus negative 1 to 1 of h of x dx plus 1 to 4 of h of x dx. What I want to do is I want to go yes, 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 no. And show that it's the 1 to 4 part that I don't have of h of x dx. Okay, so it would have been 5 plus -2 plus 7 plus no idea, which is why that one doesn't work. Okay, let's skip example 2 because I don't find it to be too necessary. The only other topic today is our average mean value theorem. And what it's saying is that, you know, if I were to go up to a rectangle, it's pretty nice because I know exactly what's happening every 1 unit. So if I look, let's say this was 1 unit, I could say, oh, it has a unit of 3, and then 1 unit is of 3, and 1 unit of 3, and 1 unit. 1 unit meaning going from 0 to 1, 1 to 2, 2 to 3. The area is pretty easy. It's 1 by 3. For other ones, this one's 1 by 5. Other ones, you know, this one's a little bit harder. 0 to 1 has a certain amount. 0 to 2, 1 to 2 has a different amount of area, and 2 to 3 has a different amount. The question is, let's take this and make it an average of some sort. So I know per unit about, on average, how much it's increasing. So 1 unit is always 1 on the x-axis. So when you're looking for an average, that's really what it's telling you. So it's saying balance it out and figure out how much, whenever you go over 1 unit of x, how much you get as a result for y, like in terms of area. So all we're going to do is do our exact, here, cover this up for a second, ignore this right here. What you're going to do is do your integral, and then you're going to divide by how wide it is, which is 1 over b minus a. So this right here, let's say it's 3 wide. Divide by 3 minus 0, or 4 minus 1, or 5 minus 2. It'll give you 3, and then you just divide by 3. So let's take a look. This one is 3 wide. This one is 3 wide. This one is 2 wide. So you would do 7 minus 5 and get 2. Don't do 5 minus 7. Do 7 minus 5. Always do greater number minus lesser number. Right? So you'll get a positive value that you'll divide by. And that's what that theorem says. It just says you can multiply it by that to find its result. So applying it, okay, so applying the definition. So what I'm going to do is I'm going to go from 0 to 3 of 4 minus x squared dx. Okay, but what I also want to do is I want to find 1 over 3 minus 0. Or in this case, what I want to do is 1/3 of this. And the reason why I want to do 1/3 of it is because I want to find out, on average, from 0 to 1, 1 to 2, and 2 to 3, how much total area is there, because it changes for every location. Okay, so nice thing is I'm going to let you use a calculator for these, or you can use the integral calculator that's on the web. So if you're using a calculator, I have it on the next slides. You'll see how to get to it. Let's see. You're going to use your math key. So you'll click math, and then you'll click F9, right? So you'll click F9, and then you'll type it in. So you want to type in your lower bound, your upper bound, your function, and then dx. Okay, that's one way of doing it. Most of you probably don't have a graphing calculator at home, and that's fine. So what I'm going to do is I'm going to show you, if you go to your integral calculator. So integral calculator, and you can actually type in your integral that you want and you can evaluate it. So let's go here. I'll show you how to do it. So options, you always want to go to options and you're going to set your lower and upper bound. So integral calculator.net, your lower bound is 0, your upper bound is 3. So 0 and 3, okay? You don't need to check off anything else. So you have 0 to 3, and we were given, why they give such a complicated, like, geez, okay. So it's definitely 4 minus 4 minus x squared, x to the 2. Okay, I hope that didn't get cut off in my video. So now you have 4 minus x squared from 0 to 3. Just hit go. Let the calculator do the work. And you get the value of 3. So it found the antiderivative for you. It's going to ignore plus c because this is a definite integral, not an indefinite one. And we get the value 3. So I'm going to say that this is equal to 1/3 of 3, which is a value, which is 1. So we want to write this finally. We're going to say the integral from 0 to 3. Oh, you know what? We'll just say the average is 1 unit. The average is 1 unit squared because the area. All right. We don't need to answer the second problem. I'm not going to ask you that. It will. Most of the time it does because it has to balance itself. So it would cross that average at some point. Okay. And that's it. So these are your homework notes. Again, don't try not to get too tricked up on them. You got a few pages of them, but that's all you have to do. Remember that the average value ones you're going to use in your calculator. Okay. Whoops. Those you're going to do in a calculator. Anything like this you're going to do by hand. Okay. Good luck. And make sure you submit them to Google Classroom when you're done.